Hi, and welcome to Module 2 of Video Lecture 2. This is the second part of a several-part series on functions. In the first module, we talked about the definitions of functions and sort of some main properties. Here we're going to discuss some additional properties of functions. The easiest way to start here is by just drawing a graph of a function and then identifying the various things we're going to be talking about, and then we'll give more formal definitions of those things. Okay, so let's do some graphs. So the first definition is the minimum or the maximum of a function. These mean pretty much exactly what we're used to in English. If I draw a function like this, and say it stops here and here, that's the domain. The minimum of the function is either here or here. Here we can draw this a little further down. The minimum is down here. The maximum is up here. And as you'll discover when we talk about Chapter 8 for the stuff on optimization in Part 2 of the class, this is a local maximum and this is a local minimum. But the minimum and the maximum of a function are the points which the function is least and greatest respectively. So if we want to work this out, we would say the maximum of a function is the point at which all other points of the function are not as big as that, or no bigger. So formally, the maximum might look like this. Function maximum of f of x is point at which all other f of y is no bigger than f of x for all y in the domain. So it's the point x at which, and I'll put a star here because that's probably easier to distinguish. It's the point at which all other values of the function are no bigger than the value at the maximum for all other values in the domain of the function. The minimum, you just reverse that. So it's the point at which all other points are at least as big as that point in the whole domain of the function. That would be the minimum. You reverse that like that. So the minimum is the low point, the maximum is the high point. Sometimes you'll see a variant of this called the argmax. It's not some weird new word, it's just a combination of argument and maximum. Sometimes people call the thing that the function is a function of the argument of the function. So this is the argument of the function. The argmax returns the argument at that maximum. So if the maximum is at over here, the argmax is x star by itself. So the maximum is the point at which it's highest. The argmax is the point that makes it the highest. So so the maximum might be this point over here. Maybe it's like 10. And the argmax is the x that makes it the maximum, which may be 4. So that's the max. This is the argmax. That comes about in game theory, less so in statistics. Okay. So there's a max and minimum, and again, they mean just like they do in English. You spend a lot of time in this class trying to compute maxima and minima when you start doing calculus and optimization. Optimization is incredibly important in the social sciences, both in game theory and statistics, and one can view actually the entire point of going through calculus, well, not the entire point, maybe about half the point, as getting to the point of optimization. Some other properties. This is an increasing function. That seems should be pretty obvious. It's going up. Increasing functions increase. Their values, as x gets bigger and bigger and bigger, as the argument increases, the values of the function increase as well. Now, unfortunately, there are many ways of saying that. If you just say increasing, it's actually fairly vague. Strictly increasing means no matter how little you change x, no matter how little you increase x, the function increases as well. This is a strictly increasing function. It's increasing for all values of x. This is also a strictly increasing function. These are all strictly increasing functions. You may also be weakly increasing. What would that look like? Well, that's supposed to be flat. Here, we try that again. Try to tell flatness in this tablet that's kind of at an angle. Here, it's strictly increasing in this range. Let me try. It's strictly increasing over here. It's strictly increasing over here. And it should be flat in this blue range over here. That is a that's a function that's weakly increasing. A weakly increasing function never decreases. Increasing functions are used whenever you're trying to represent something that's increasing. So if you're trying to make the argument that democracy increases GDP, then you should have democracy be your x, and as you get more and more democratic, you should have higher and higher GDPs. That function should be increasing if your theory is correct. As you might guess, you can also use strictly decreasing and weakly decreasing. Here's a strictly decreasing function. Here's a weakly decreasing function. Again, same idea for both. A strictly decreasing function decreases always as you increase x. A weakly decreasing function never increases as you increase x, but it can stay constant for a while. If I were to say decreasing or increasing by themselves, it's actually kind of vague. It might mean strictly increasing, it might mean weakly increasing. A monotonic function is generally an increasing function. Sometimes it's referred to as a strictly increasing function or a strictly monotonic function. These are all words that come up a lot when you're trying to represent preferences or other things by functions. Monotonic, increasing, decreasing, all help you understand the shape of the function and what it's actually representing. Okay. Okay, now moving away from graphs for a little bit, we can talk about some other properties of functions. Functions, in general, you can do a lot of stuff with functions because you could, as you could with anything else. If a function is like this, so it maps onto the real numbers, then f of x is just a real number, so you can add them together. You can multiply them, and so on. Whatever you can do with numbers, you can do with functions. There are a few additional things, though, you can do with functions that you don't have with numbers. The most important of which is function composition. Write that out. Function composition. Composition can be written one of two different ways. My preference, and the one you'll see in this class almost throughout, is to do this. What this means is f is composed with g. That's how you read it. F composed with g, or f of g of x. So really, it's the reason I like this particular arrangement of notation is that it's very clear because it tells you what to do. What this means is, first, take your argument x, plug it into g to get g of x. Then plug g of it that you just got into the argument for f to get f of g of x. This is how that would work. Let's make them all real numbers for the moment to make life easy. Let's say f of x equals x squared and g of x equals x plus 3. Well, what would f of g of x be? Well, it's f of x plus 3, because first I plug in for g of x, and then you do it again, and you plug in, what's f of x plus 3? Well, it's x plus 3 squared. Now let me take a step back, because this can be confusing for people who haven't seen this before. When you say the function is x squared, what you're saying is, take whatever argument I have in my function and square it. it doesn't have to be just x. X is a stand-in for anything. So if I take the number 7, I square it. If I take yzr, I square it and get y squared, z squared, r squared. Whatever I put into my f, I'm supposed to square. That's what the function means. So in this case, I put x plus 3 into my f and square that. I could expand and discover that f of g of x would then be x squared plus 6x plus 9. Function composition allows us to make more complex functions out of simpler ones. Let's try again. If f of x equals e to the x and g of x equals the square root of x, then f of g of x equals e to the square root of x. Right. It's a fairly complicated function. I couldn't draw it for you right now, but you can write it pretty simply out of these two component parts that we could draw that are simpler. That's function composition. The other way of writing it is to use an open circle between the two. So that's actually a f of this little circle here, g of x, maybe a little smaller circle, make it more clear. I find that notation unpleasant, so I'm not going to use it ever in this course, but you will see this in math and possibly other stuff in political science, so you should be aware that open circle means composition. One final thing to be aware of, you can't compose any two functions, right? If you're composing the function f of g, and f is a function that takes you from a to b, and g is a function that takes you from c to d, then d and a better be the same thing. Why? Because if you do this, well, you plug in a d for x, you plug in a c for x, you get out something that's at d. If that set d is not the same as the domain of f, then you haven't defined your function on the right domain, and you can't take the composition. So here, a must equal d. The range of the function g must be the same as the domain, or at least a subset of the domain of a. So at the very least, this could be true. At the very least, d must be a subset of a. That's more accurate. D must be a subset of a, otherwise you can't actually do the composition. So be aware of that. Why do we want to care about composition? It relates to the function inverse. Well, there's a lot of reasons why, but one reason is the function inverse. Before we get there, we need a couple more definitions. We talked a little bit about identities before. I mentioned there are functional identities. This one is really easy. The identity function is this. It means you take whatever you're given and you keep it, right? F of x equals x, so whatever argument you're given into your function f, it stays exactly the same. So, and that's important, right? You want this is a way to keep whatever you have the same. Okay. Why do we care about that? Well, we care about that because sometimes we want to undo what we've done with functions. We want to change our function back into the identity, right? So say multiply by 3, but want to reverse that effect. Well, we can reverse that operation by multiplying by 1 over 3. That's the multiplicative inverse. Here, though, for functional inverses, it's a little more complex. And to actually try to find them, we need a couple more definitions. There are two common definitions that are really used about functions. The first is called surjective or onto. And what this means is the function fills the entire codomain. So every single point in the domain maps to a point in, well, the whole codomain is covered by points in the domain mapped to it. In other words, if you're making the function f of x like that, then the range of the function is the same as the codomain. You're covering all the points. The range of the function covers all the points in the codomain. So for instance, this function right here is surjective. It maps across the entire real line. Right. On the other hand, this function is not surjective on this codomain because it maps only to the non-negative numbers. If I change this to here, including 0, it would be surjective. So what codomain I define changes how I specify whether or not it's onto or not. So that's one thing. And again, don't worry if you don't see why I'm doing this yet. It'll be clear in 1 second. The second definition is injective. An injective function is one-to-one. A one-to-one function has one value of the range for each value of the domain. So this function is one-to-one. For every x, I get a unique value in the range. This function is not one-to-one. -1 goes to 1, and +1 goes to 1. So the same number goes to 1. So two different numbers go to the same number. That's not 1-to-1. That's 2-to-1 in this case. So this thing would not be injective or 1-to-1. Here's a good time for a side, by the way. All functions have the property. Not all functions are 1-to-1, but all functions have the property that for each point there is only one point in the range, right? So two different points might map to the same point in the range, but each point in the domain maps to only one point in the range. And I apologize if I said that wrong. Each point in the domain maps to only one point in the range. So here f of -1 maps to 1, only 1 point. F of 1 maps to 1. Same point, but still only 1 point. There are ways of writing function type things that map to more than 1 point. For instance, it might map to the set 1, -1. That is called a correspondence, and it's not a function. Functions must take each point in the domain to one and only one point in the range. A correspondence maps one point in the domain to possibly more points, one or more points in the range, so a whole set of points. We generally write it like this. I should not use the same thing for a set. With two arrows. And you map each point in the domain to more than 1 point, possibly more than 1 point, a whole set of points in the range. That gets much more complicated. It's primarily used in political science in game theory, because when you study game theory, you calculate things called best response functions. And sometimes, if you're indifferent between more than one thing, your best response to an action might be a set of things. For instance, if you give me $1 no matter what I do, then my best response to you is anything. All my actions are equal. So my best response correspondence is a set of anything I might do. That's a correspondence. It's generally much more complicated than a function. It usually has very analogous definitions to functional definitions, but it's more complicated because you have to deal with whole sets at a time. We are not going to talk about correspondences in this course, but if you're interested, you can go on and study them at your leisure. Particularly in game theory, they come up a bunch. But here again, we're going to focus on functions only. Okay. And a function again is something that maps a single point in the domain into a single point in the range. Okay, so far I've done injective, which not only maps a single point in the domain to a single point in the range, but each point in the range is mapped by one and only one point in the domain. So, graphically, right, we said this is a function, a one-to-one function. This is not a one-to-one function because this point is mapped by two different points in the range, here and here. And this, by the way, is a correspondence because points in the domain are mapped to two different points in the range. So one-to-one function, function but not one-to-one pointing at this. One-to-one function, not one-to-one function, and not function. And if you're wondering at home, by the way, why I'm cutting off various words, just because my tablet I'm writing on is about 13 inches, so I can't use an entire whiteboard like I would normally do. Okay, so that's those definitions. Now, finally, why do we care about these? Turns out, if you're both one-to-one and onto, so surjective and injective, reversed, injective and surjective, one-to-one and onto, then you're what's known as bijective. One-to-one and onto. That means that for every point in the domain, you get 1 point in the range. For every point in the range, you have one and only 1 point in the domain, and the entire range is and the entire codomain is covered by the range. In this case, you have what's called an invertible function. An invertible function is one in which you can reverse the action of the function. You can take a function and reverse it, getting back again the identity function. In the exact same way, you could take a 3 and multiply by 1/3 to get back to 1, the identity. We call an inverse function f to the negative 1. Now this is important. This is not the same thing as this. This would be represented by this. And I should say at this point, we'll talk about it more of functions, but a negative power means you do 1 over the object. So x to the negative 1 is the same as 1 over x. We'll talk about this more when we do polynomials shortly. This thing is defined as an inverse function and has a very particular characteristic. The characteristic is this. The inverse function composed with the function itself produces the identity function. That's it. If you compose, and this works both ways, the function of the inverse function is also the identity function. This defines the identity function, and it can be extremely useful. Let's do a simple example. What's the inverse function of 5x minus 7? Well, it's the function that when you plug this into it, produces x. Well, let's see what we do there. Well, if we first add 7 to this, then we'll get rid of that negative 7 right here. And then if we divide by 5, we'll get rid of this 5. So let's call the inverse function x plus 7 over 5. And we can check that like so. First, we want to calculate, well, I'll do it fresh. Okay. So we had 5x plus 7 was f, and f inverse, and here sometimes I'll drop the x, the of x, it's understood in this case, equals x, oh, sorry, this was a minus, start again. I'll put the x back. F of x equals 5x minus 7, and we're saying the inverse should be this, x minus 7 over 5, plus 7 rather. How do we check that? Well, first let's do f of f inverse of x, just cause. Well, f inverse of x, that equals f of x plus 7 over 5. How do I compute that? Well, we plug this thing into the argument in f, so this whole thing gets plugged into there. So we have 5 x plus 7 over 5 minus 7. The 5's cancel. You get x plus 7 minus 7. That equals x. So that works. We can do the reverse now. Now we have f inverse of f, which is 5x minus 7. Again, we plug this thing into the x up here, and we get that equaling 5x minus 7 plus 7 divided by 5. The 7's cancel, the 5's cancel, and again you get x. So it works both ways. So in this case, we've calculated the inverse function for that function, and that returns the identity function. We've basically reversed the machine. We've counteracted what the machine of the function did to the function itself. In general, it's not that easy to calculate inverse functions. We'll discuss some inverse functions when we give examples of functions shortly, but they are very useful in various contexts we'll get to over the course of this course. Okay. So that's it for this particular module. Thank you, and I'll see you soon.